very quickly, so Keith mentioned about the International Windship Association. I'm going to assume many of you know a fair bit about what we're doing, know a fair bit about wind propulsion, but there are slides on here that have some more technical information, and we're always, you know, there's many layers to that. So if you need more technical information, just let me know. But yeah, we're actually over 150, probably more like 200 now, active members, and we have a very much bigger network as well, probably a couple of thousand that receive our newsletter and also interact with us. That is an organic membership. We've never gone out and actually recruited members. So it's very organic, and there are actually many ship owners who are not members that are actually interacting with our membership. So I'm going to talk about wind propulsion and how that's fitting into the policy structure, if you like, or the targets that we've got first of all. Then I'm going to move on to some examples of where clusters of development are happening, and also we'll look at the market, where it is at the moment, the forecast going forward. We're going to round that out with some trends and developments in there, and also some barriers and drivers, which we didn't get. Last time I was here, we did a forum back in September. We discussed some of these. We'll have a little bit more of a discussion on this. But yeah, so the IMO, I think you're all pretty aware of what happened in July, MEPC 80. We had some indicative checkpoints, targets. That's the way I look at it. You put a number on something, that's a target. It doesn't matter what you call it, it's a target. So 2030, 20% striving for 30% from a baseline of 2008, 2040, 70% striving for 80%, and then 2050, the net goal. I always find nets are very leaky. I don't like net zero, zero emissions. That's what we're aiming at, and that's what we provide. Wind propulsion is providing not just zero emissions GHG, zero emissions, period. A couple of points I just want to highlight around that strategy. So initially, the strategy was all about fuel. Yeah, 5 to 10% zero emissions fuel was going to be part of that strategy. Well, the 5 to 10%, 5 striving for 10% was included. But if you read the text, and the text on the next page, which I won't dwell on, it actually includes energy and technology as well. That's fuel, energy, and technology. This includes wind propulsion. So now we have a target that we are included in that thing. Now, that's actually a staircase, okay? A never-ending staircase, which is pretty much how my life feels sometimes. We actually see those targets there not as a ceiling, we actually see those as a floor. Yeah, we've got to go quicker, in my opinion, and I think in most of the people's opinion that understand the science. That 2030 target of 20% is not enough. 30% is still not Paris climate 1.5 aligned. Need to be around about 40, nudging up to 50% reductions by 2030 in 6 years if we're going to align with Paris. And Paris was the lowest common denominator on the climate agreement. So we've got a massive ask. If we look at LNG alone, 20 years of LNG rollout, 3% of the fleet. Yeah, I mean, that is a big ask. But wind propulsion can provide some activities. And actually a CE Delft report that was released during MEPC 80 looked at, with some parameters, which I won't go through, but there's a link to the report on this, basically said that using wind plus speed, not voyage optimization, only speed, there are other benefits that could be used, plus energy efficiency measures and eco-fuel at around 5 to 10%, we could be delivering 28 to 47% emissions reduction by 2030, pretty much excluding the eco-fuel, using everything that's on the shelf today. And it would only that would increase the cost of shipping between 6 and 14%, which is within the bunker variation levels. So we're talking, this is absolutely doable, but we've got to pull our finger out and get moving on it. So that's, I'm not going to go through that. That's for your information later. I'll give you the PDF. But that just basically explains what I've just been talking about. So direct application of wind power. Okay. I still have to explain this to people in the industry. It's unbelievable. The wind is used to move the ship directly, not all the way through the process. So the top process, wind is delivered to the turbine, all the way through to the power coming out of the propeller. You're losing 9 units out of 10 of that power. So 90% of that power loss. You deliver that to a ship. Okay, we can have an argument about how much is translated into propulsion, but basically you're getting 100%. Yeah, it's moving the ship with the wind. And if it doesn't move the ship fast enough, well, then we get into a business discussion. But we move ships. Now, something I put into the abstract. I want to just talk about some. Those things are pretty clear. Yeah, it's a zero emissions energy source delivered directly to the ship without having to mine it, refine it, transport it, bunker it, or store it on the ship. So all of that infrastructure is not required. But there are also some co-benefits that we don't often talk about. One of those, which is rising up the policy framework, if you like, is underwater radiated noise. Now, of course, if you're delivering wind to a vessel, you can maintain speeds, reduce your propeller, or the power going through your propeller. So you can actually move it from the cavitation area into the no cavitation, for example. Now, this was a study done by one of our members, and they actually looked at a couple of simulations. One was 100% conventional propeller propulsion, the other one was 60% conventional, 40% wind propulsion. Now, we don't call that primary wind, but it's close. This is a major wind-propelled vessel. And one of those is potentially the canopy, which you'll see a picture of in a moment, which is installed with an IRO system, and that's transporting rocket parts from France to French Guiana at the moment. Now, the decibel, actually you can't see at the bottom there, but that's okay. The decibel level basically reduces by about 14 decibels. Now this is, I think, selected, yes, the 100 hertz level. 100 hertz level has major disruption to fauna in the ocean. Now, most people think, oh, underwater radiated noise, that's affecting whales, large mammals, but it also affects phytoplankton. Now, when they are stressed, they don't create their shells. They don't sequester the CO2, the carbon, and that causes another climate impact. So it's not a greenhouse gas, but it has a climate impact. We're not sequestering as much carbon in the oceans as we should do, partly because of the underwater radiated noise. So, one of the case A vessels, the propeller, 100% propeller, basically works out at the same underwater radiated noise of 25 of these canopy vessels at 40% wind, because you're reducing by 14 decibels, and it's almost exponential. So a 14 decibel difference, I think, is basically like, for example, a hairdryer going to a rocket engine. Yeah. And this stuff, if it's in certain areas, can travel for a very long distance. So it's incredibly disruptive. So this is one of the co-benefits. Virtually no study has been done. There's very, very little around wind compared to propeller stuff. But there's some other considerations. I'll just quickly go through this. The middle one is very important for IMO with the MPAs. So there's an attempt to create 30% of the world's oceans will be marine protected areas. Now, you won't be able to go through those marine protected areas or close to them with high-speed vessels of any kind because of the underwater radiation noise in the future. At the moment, that's not a problem because we don't have the regulation. But this will actually mean that you would have the option to go silent or near silent by going fully wind around those areas when you're going across whale migration routes, etc., etc. This is becoming a bigger and bigger issue in the RINA. Range extension. Just as an example, there are very, very concentrated areas of activity. You know, the Malacca Straits, the Red Sea, as we're seeing, which is not very congested at the moment. I can't imagine why. You know, the English Channel, for example. These are choke points. These are incredibly noisy areas. So if you've got a wind system on board, you've actually got almost unlimited range, but you've certainly got a range extension. So going around the Cape, for example, is possible to do at a much reduced cost if you've got wind propulsion on the vessel. But you could also, for example, go around Sumatra as opposed to going through the Malacca Straits. So we could actually divert ships to reduce the underwater radiating load. That gives us tools in the toolbox to use. Now, okay, so talked about one of the co-benefits there, and there's always discussions around these and dissent on those things. But I'll just talk about the market forecast and policy pressure. 2023 was a busy one. Now, we did a survey in June, and what we asked policymakers, these were ship owners, stakeholders. This is just the result of the stakeholders, and sorry, it's a bit small. I forgot how small this was. So, but what it's very simply saying here is all of the fuels usually are surveyed. And actually, I've checked with most of the surveys that have gone on with an energy mix where the ship owner is allowed 5 options. They say that's going to be methanol will be in the energy mix in 2030. So will biofuels. So will HFO. You only have 5 options to choose from. Okay. Now, wind is almost never put into this, so we put it in. And what we got was wind assist by 2030. So wind assist is sort of 10, 20, possibly up to 30% of your power derived from wind. That's a wind assist, yeah? You're helping your engine. That was significant for 2030. It was pretty much at the same levels as HFO or methanol. Saying that will be a major part of the energy mix in 2030. But by primary wind was very small. But by 2050, actually a lot of people were saying wind assist and primary wind would roughly be the same as part of that energy mix. So combining those, it becomes an incredibly significant propulsor. Now, a lot of the industry still says, oh, but wind, that's an energy efficiency measure, isn't it? No, it's not. An energy efficiency measure cannot move a ship. Yeah? Air lubrication is an energy efficiency measure, yeah? It reduces the energy. Wind moves ships. Now, you might only get 1 or 2 knots. You want to get up to 12 knots or 15 knots? Well, that's a commercial decision or possibly a safety decision. It still moves the ship. It's an energy force. So, and this was the same across all of the segments that we surveyed. Policymakers, ship operators, ship owners, and other maritime stakeholders. Now, where are we at the moment? Well, actually today, we have 33 large commercial vessels in operation with wind propulsion on them. That is about 2 million deadweight tons of ship. That sounds a lot, but it's not, as you know. It's still 0.001%, something like that. But we're basically where LNG was, if you take the tankers out, after about 7 or 8 years of development. Okay, so we're making progress. But also there are 11 wind-ready vessels and another 16 in the pipeline for delivery in the next couple of months. So we estimated a doubling from last year, which was 23. By the end of 2020, the end of 2023, or the first couple of months of 2024, just because logistics issues, etc. We're pretty much hitting that. Now, I'll talk about where we're going next, because you'll see this, actually the one on the left, this, the bottom left, this graph here, this is from an EU forecast in 2016-17, looking at bulkers and tankers. And pretty much by 2030, we deliver up to 10,700 ships. The UK government then expanded that out to 2050, said roughly 40 to 45% of the global fleet would be wind installed. That's primary wind, new builds and retrofit. We think both of those are pretty conservative. We think it could be well above that. Virtually 100% is possible with different systems on different types of vessels. So the future, and by the way, the pipeline coming through, we're looking at doubling that number again this year. So we're on that cycle of doubling installations every year. Now that line there, that's the one from the EU and the UK estimates. As you can see, 2030, we've got the checkpoint there. All of these developments, the EU developments, EU ETS, 2 weeks ago, introduced. Fuel EU Maritime, which has a wind component within it, a wind bonus. It's only small, but we're pushing to increase that. That will be January 1st next year. CII, obviously, probably a few of you went to the CII conference over at IMO the last couple of days. That's enforced the EEDI, EEXI. All of these, not one of these levers is enough. But collectively, what is this saying to the industry? This is saying you've got to move. You've got to move, and you've got to move now, because this pipeline is pretty much unstoppable. Now, do we all like CII? Let's have a show of hands. Are we CII supporters here? That's a surprise. There are problems, there are issues, there are challenges here. But the overriding issue is pressure, and it's upward pressure, price pressure, regulatory pressure. And this was a thought exercise that I did, and we can't see the bottom bit, but I'll explain what it is. This was a thought piece that I did back in 2021. Just basically said, if we had wind propulsion on every ship mandated by 2030, we could deliver around 20%. 20% reduction with a bit of voyage optimization. Okay, that's pretty conservative actually, but we'll go through it. The fuel cost that would save would equate, and this is slightly updated with new numbers for the cost of fuel, would be deliver about 1.3 trillion in savings by 2050. UMass and UCL estimate between 1.4 to 1.9 trillion for the total decarbonisation of shipping. Now, remember, if you're using wind, you're using 20% less fuel, potentially less infrastructure, maybe less storage on board. So you're actually reducing that total cost as well. So in effect, wind propulsion put on every ship by 2030 could deliver and pay for decarbonisation of the entire industry. So we can have it for free. Not quite, you know that. And you can always challenge me on that, please do. That'll be a fun discussion. So where are we at the moment? Well, our feeling, and Greg actually at the back here sits on my executive committee, so he's heard me spout off this a few times. We are feeling, or the feeling from a technological point of view, but also from a market point of view, is we're reaching the inflection point in the S-curve. So we've been pottering along here, an installation here, an installation there. A couple of installations. Oh, we're now at 30 demonstrators. Now we're starting to see fleet orders. We had 6 wind-ready tankers delivered to a Greek ship owner this year. Yeah, foundations are in, everything's in, they just don't have the systems on yet, they're waiting, for some financial indicator, maybe they didn't have enough to go for all of those, but they're wind ready. This is a notation by AWS. So the radar changes have been made, the navigation changes, foundation, all of the aspects around wind have been factored into the build of those, new ships. So we're feeling that we're roughly at that inflection point. So I've talked sort of macro. Now I just want to give you an idea of some of the development that's happening. Some examples, some regional examples. This is actually a ship. Sorry, that picture isn't very good. This is a primary wind vessel that's been designed and built specifically for the Marshall Islands, for domestic shipping, and it's funded by the German government. That will be in operation from March, and this will be probably a model or a template for many, many more of these ships. And actually during COP28, IWSA put out a call to the global community saying, fund an SDG 17 delivery fleet. If we could unplug the whole of the small island developing states in the Pacific, for example, 15% of the planet, of the area of the planet, we could effectively unplug them completely from fossil fuel shipping, reduce costs, increase jobs, but I'll talk about that a bit in a second. And that's what this is all about. So creating a virtuous circle. Now, whenever we talk about shipping, we're always using fuel costs, say the Singapore cost of fuel. Right. Majority of shipping, that's true. The problem is, we move to Fiji, and then that price, that fuel has to be tankered down to Fiji. It costs $1,100 per ton. But that has to be paid for in US dollars. So the Fiji national currency is far lower in value, the purchasing parity of that currency. So we're not just talking about higher costs, and that's in the main port in Fiji, not one of the outlying islands. But they're also having to use their very, very expensive foreign currency reserves to pay for that. So it's actually costing them double, triple. Now you go out to Wallis and Futuna, which is a small island, about 1,000 miles away from there. It's $1,800 per ton. And their economy is even weaker than the Fijian. So they're probably paying 10 times what we're paying. So on the periphery, already shipping is completely unsustainable. So it's not a matter of can we afford the fuel, is we have to get enough passengers on the boat, take their money, so we can actually go down and buy the fuel. And I've sat on boats for 2 days, waiting for enough passengers to come up to pay their money so we could actually fuel the boat. Yeah? Or there just simply is not a boat. There are no boats, there are no ships. So what we're looking at is if we were able to bring in a low fossil fuel powered fleet, we can also create virtuous circles or virtuous cycles. We can actually have co-design fabrication of the systems on these islands in Fiji. Then we can actually create employment, skills, etc., but also aspiration. The young guys, these are people that have grown up around the sea, that have no opportunity to actually earn a living from it. Now they can get involved. And then we also can open up new routes that are uneconomical if you've got fossil fuel, or alternative fuels which are likely to be more expensive. And I remember going in, when I was in the South Pacific, we had a design for a ship, we'd done all the business modeling for the ship, we went into the politicians and we said, right, we're sorry, but we can only make $10,000 a year from this shipping line with this ship. And they were like, $10,000? That's ridiculous. That's so low. We're not interested. And we talked to them for about another half an hour, and we found out that their calculation was with the 84% subsidy that the government was going to give us. So they thought we were only taking 10,000, but we hadn't included that subsidy. So with the subsidy, we were making a huge profit. So one of the problems is the whole economic cycle is under a huge weight of fossil fuel and the cost of fossil fuel. So there's a lot of small vessel, traditional vessels that are being designed. Some of these are in operation on the top left. You've probably seen these in books that you've read for many, many years. But we're starting to see new systems and new ships coming through. Actually, all of these cruise vessels here and these fishery vessels, these are all new or relatively new installations. So we've got the technology, we've got the know-how. It's simply pushing the button. And frankly, these systems and structures will pay for themselves. Now, let's move on to China. Let's go to the other area. Big ships, big shipyards, fantastic. Yeah. Whoa. Retrofit. Well, in the last, I think these two. The first one, the new Vitality. This is a VLCC built in 2018. This one was built in 2020. They've been in operation for quite a few years with wing sails on board. We've had all these other installations have been in the last 2 years. Chinese yards now, so I'm not going to go through all of the details of these ships, but the yards now are starting to understand what wind propulsion is. They're starting to add wind systems onto their standard lists. So my father-in-law used to be in shipbuilding. He said, "Oh, it's great when somebody comes in and says, we'd like something special on the boat." Zero on the end of the cost. Yeah. Once these systems are on the standard list and there is a learning curve, there's an understanding of these systems, prices start to drop. The barriers start to remove. And I'm sure you're all naval architects, I don't need to tell you about that. If it's standard, if it's a bog standard bulker with a bog standard piece of technology on it, it's cheap. When you start getting fancy, it gets expensive. But China is moving on this, and actually this is the latest one. It was in December, and these are made actually in China. So this one, and this one, and those two are all Chinese-made technologies. So it's being seen as an opportunity, and the Chinese Classification Society have issued their guidelines. We have BV, DMV, LR, Class NK, RINA, and now the Chinese guidelines are there as well. A big development in Europe is our cluster in France. So all of these are indicating companies that are developing or involved with the development of wind propulsion in France. They've plugged wind propulsion into their blue maritime plan and increasingly looking at this as an opportunity. And I think they're talking about by 2030 having about I think the numbers I saw about 3,000 to 4,000 jobs solely in wind propulsion technology. Investments are going in the tens of millions of euros now. UK a little bit behind on them. There's a shock in the maritime industry. Yeah. I'll take that back. I shouldn't discuss that probably. Finland. Okay. Some names that you're probably familiar with. All of these are members of ours. Napa, Wärtsilä. I think probably a few of you have heard of Wärtsilä. They're a member of the IWSA. They're looking at energy systems, not just engines anymore, wind engines, any kind of propulsion system. They're energy solution providers. But you can see this whole ecosystem is developing. In France, developing even stronger. I just wanted to show you that Finland is another area where they're seeing opportunity here. And these are all interacting and working with each other. Vaisala is actually developing, one of the leading developers of LiDAR. And LiDAR's interesting because you can actually map the wind coming into the ship and adjust your system. So if you've got big systems, which can really generate a lot of lift, a LiDAR system, which is expensive at the moment, could be a good option to really optimize those, get another couple of % out of that. Be able to retract the mast if a large squall is coming in. or depower it in advance. So all of these systems, all of these developments are coming along. Weather routing for wind, very sophisticated now. Yeah, the software is out there. We can weather route, and I was just talking with Greg actually about, you know, machine learning AI. We can now simulate thousands of voyages in a few minutes using the parameters that you want to find, are you okay with the 20% reduction in ETA? Okay, you can make big savings. You want to maintain your ETA? Okay, you've got more of a restricted area, but still you'll be able to make better choices using that software. Now, wind propulsion trends, and that's coming to the end of the major aspects, and then we'll talk a little bit about the barriers. So this is all the positive story, yeah? I'll take orders up the front. Okay, so get your checkbooks ready. We've got, okay, retractable and mobile systems that move on rails, retract down. Containerized systems that actually fold down into the container, for example. So air draft, dealing with air draft issues. Wind routing, I've just talked about. Optimization from LiDAR, but not just that. You know, weather sensors, forecasting, weather forecasting in real time. Scaling production. 3 companies have already set up substantial production facilities in China, near the yards. They're already producing tens of systems. Down here is wind ready. This is a wind ready vessel. You can see the rails for a movable rotor system. The rails are on during a dry dock, but they're not ready to put the rotors on. Containerized systems. We'll actually have, what could be any time this month, will be the first container ship with a containerized, 2 containerized systems on board, and that's 1,000 TEU container ship, so a small feeder, for one, or ONE. Is it one or ONE? The Singapore container, you know, the pink ones. Okay. Interestingly, there are I think 6 container ships which have wind and methanol being either being constructed or contracted signed to start construction in Korea at the moment. And those are between 1,200 and 2,500 TEU. The size is going up. Hapag-Lloyd just announced they're looking at a 4,500 TEU container vessel. Energy harvesting. Well, if you've got a huge amount of wind, you can't use it all. You're going to have to spill it. Because you've reached your design speed or you've reached your operation speed, you can't use that wind anymore. You can spill the wind out of yourself. But what if you're able to slow your hull down? Have some drop-out hydro generators. You know, reverse your propeller. Comes, if it's on an electric drive, becomes generator. You start generating electricity, you start producing alternative fuel on board. This is actually one designed by MOL, and this will be in operation in 2030. And she's actually a tanker that fills up her own tanks with hydrogen and stores it in toluene. So using the wind on very windy trade routes, she's actually generating a cargo, not just the fuel she needs, but the cargo as well. And then primary wind, which I've already mentioned before. And this is actually a ship that will be in operation from 2025, currently being built, 136-meter ro-ro. She's being built in Turkey. So she'll be in operation from 2025. And these were a couple of the primary wind projects. So the one on the left is what I was just talking about, the one on the right, the Wind Hunter. Ocean Bird, being developed in Sweden, 7,000 car carrier. And it's going to be operated by Wallenius Wilhelmsen, probably 2025 to 26. And Chantier d'Atlantique, these are just some examples. Building the Silent Seas, which are 210, well, it's 190 meter to 210 meter cruise ships. So these are expedition cruise vessels. They've just signed another contract with Orient Express, Accor company, to deliver tours in 2026. These are up to 70%. And those are huge masts. They've got one in San Jose, it's about 78 meters. Yeah, we're talking about producing a huge amount of thrust from that or lift from that. The issue is around stability. So they've been working on that very detailed way. Okay, so it's fantastic, yeah? The future's wind. You're all convinced, a few of you sitting there going, no, I'm not convinced. Okay, all right, well, this bit is probably the bit you'll like better. It's, what are the problems that we still have? Yeah, and there are problems, of course there are. This was part of the survey we did, and this is from the maritime stakeholders, including 19 ship owners. This is what they came out of. There's no way, yeah, finance, money. What's the problem? Money. Okay, but remember, this is a propulsion system that uses free energy. It's the only propulsion system that's cheaper than what we've got today. It will actually pay for itself. Yeah, within 3 to 5 years for a retrofit, quite possibly, it will pay for itself. So you've got free energy for the rest of the vessel's life. And not just for the rest of the vessel's life, you can take the system off, put it on another ship after the ship is broken. Yeah, if it's an older ship. Operational, yes, okay, well, the ports, many of our members are spending a lot of time with port operators talking about how, or discussing how the operation for stevedoring is going on for bulkers. A lot of dust generated by a bulker, quite often. So how does that interact with the system? But all of this is being looked at, fed in, first iteration, second iteration, third iteration. But intermittency, yeah, when, again, people come up to me, yeah, what happens when the wind doesn't blow? The whole decade I've been doing. Of course, wind can't give you everything. But it can, if, for example, we have the green corridor developments, yeah? Everyone's heard of the green corridors going on. We've always had green corridors. They're called the trade winds. We just don't use them. We always see wind as a problem. But if we harness those trade winds, that wind is pretty much blowing all the time in the direction that you want to go. And if you do the old route around the Atlantic, if you look at all the old nautical charts, you go across basically from the south of Portugal, across to the Caribbean, up the east coast of the US, and come across to Liverpool in the cycle. Problem is we're not trading slaves anymore, we're not trading cocoa anymore, we're not trading gold anymore. We're trading other things. But that was the old system. That was the way that we did it. We can do it again. Technical integration, installation. Well, a lot of the technical problems, yes, there are issues around stability and etc., and we'll come to those in a moment. But a lot of these are now being fixed, or we know what the solutions are, and we're working towards them. And we've got now hundreds, if not thousands, of people working with this stuff in research institutes, universities, in the OEMs themselves, in shipping companies. Everything is being fed back. There's a massive feedback loop going on there. And IWSA has just released a safety analysis of wind propulsion. About 200-page report, if you want to read it. They do a bit of economics in it, but the safety stuff highlights basically the issues, and their finding was pretty much saying there are no major issues that we don't have solutions. There are major issues, but we've got solutions. Okay, and then verifiable results. Well, that's a problem. At a design stage, yes, we're pretty good. But once you get up to the commercial level, nobody wants to share their data. Surprise, surprise. So we're encouraging our members to share as much as possible. Policy regulation and perception. This is a disruptive technology. Yeah? This means new business models. Some people are going to get wealthy out of this, some people are going to lose a bit. First movers, late adopters. All of this is disruptive. And I think we're very much in a disruptive period in shipping, alternative fuels. Pretty much everything's up in the air at the moment. And wind propulsion is part of that. But the great thing is, wind propulsion compatible with anything else you do. If you want to go for methanol, knock yourself out, but put wind on it as well. Ammonia, fine. Wind and ammonia works perfectly well. Wind and nuclear, haven't worked that one out yet, but give you 6 months and I'll. Okay, so these were some of the, we had a big round table, about 35 experts, I think it was, 30 shipping experts plus, all getting around looking at this from a technical point of view. This was the technical roundtable results. Diffusion of tech know-how. Well, 2026, this was when the European Union did an assessment. That was red. There was virtually nothing. We're now pretty much, you know, yellow to green or amber to green. Yeah, we're getting there. The technical know-how is there, but each application, each type of ship, each system has variation. The class guidelines, pretty good now, but they're pretty good for wind assist, for primary wind ships, not so great, because we don't have them at the moment, or we have very few, but they're not commercially active. So we've got a few cruise ships that are, but we need to have bulkers that are primary. Primary wind's 50 plus wind power. Third party verification, we're getting there. ITTC is working on performance standards. We need better training. We need most of these systems are fully automated. You don't have guys with rigs going like this. You will do on smaller ships. It's automated, but maintenance side, understanding emergency procedures. These types of aspects certainly require training. We are developing training programs, and we will be even more this year. The integration and support systems for WPT. One of the problems is we're putting wind propulsion systems onto ships that are not designed for wind propulsion systems. So integrating that system into the whole energy management system of that ship, its rudders, its engines, the power curves, I mean, that's difficult at retrofit. We're getting better. You know, it's not Man Diesel anymore, it's Man Energy Solutions. They've developed, you know, software that can move between energy curves or power curves, because sometimes you're getting no wind, sometimes you're getting 100%, and then you're down to 20%. And that can be happening in the space of 10 minutes. So you've got to have a system with your engines to keep them efficient. They've got to be able to switch and deal with those different loads. You know, when you're delivering a lot of wind, you've got a lot of side or leeway force, yeah? Just when you need your rudder to be really powerful, really strong, you've got less propeller wash going over that rudder, so it's becoming weaker. You've got to put more rudder angle. So it's developing those. For example, the gate rudder systems are being tested at the moment in combination with wind. So solutions are there. Now moving on to the policy regulation, I've talked already quite a lot about this. We are doing better. We've got a strategy for decarbonising shipping. Yeah. Is wind included in all the regulations? No. Why? Because all the regulations were written for fuel-powered ships. Yeah? Fossil fuel-powered ships. All of those regulations, just as we're having to rewrite the ammonia or guidelines to allow ammonia or hydrogen or methanol. All of this stuff is underway. It's all got to be reconfigured, but wind is different. Yeah, wind is special. I like it. But all of this regulatory framework has to be revisited and ensure that it's a level playing field, and that takes time. But we're getting there. The principles are already there. We just got to develop that a little bit further. Fuel prices, I can't do anything about that. Although I was in a meeting with a large oil producing country, and I said, well, you know, bunker prices, yeah, there's nothing we can do about that. The transport minister lends in and maybe we can do something about it. I thought it was very nice. Skepticism and perception. This is still quite a big issue. I still get the occasional person from the industry saying, Oh, you're the guy that doesn't want to have engines in. Where did that come from? And these are people that have been in the industry for 20, 30 years. So you think, okay. But there's still a perception around wind. It's a little bit like nuclear. If somebody says nuclear, some people go, oh, great, the future. Other people, dangerous. Don't want that. Chernobyl. Yeah, that's a big perception problem they've got. We've got the problem, didn't we do that for 5,000 years? Wasn't it bad and therefore we changed the fuel? No, it wasn't bad. It's just, and you can get, if you want me to bore you for 3 or 4 hours, talk to me about this issue. That transition from sail to coal or steam and then onto oil is a very misunderstood period of history. And I'm a historian as well, so it didn't happen the way most people think it happened. It actually happened. Anyway, okay, I'm not going to go down there. Sideline, but if you want to talk to me about that, I'm here all day. Okay, so moving on to business operations and finance. Now, this is really where we're coming down to the crunch time. Because we've got ships going in, we've got fleet, installations. The finance industry doesn't understand wind because it's free. It's free energy. How the hell do our models work when we've got free energy? Because even when you put free energy through a turbine, it produces a commoditized electrical unit that can be bought and sold. Wind doesn't do that. How the hell do we make money out of this? Yeah, you can sell the kit and then it's This issue is an issue that needs to be developed, and we need to be educating the finance world better. The insurance industry, again, don't quite understand what this is. There's still perception, oh yeah, windships, the wind doesn't blow and then they sink, or the wind's really heavy and just knocks onto the rocks and you're in all kinds of trouble. There's still perceptions out there that have problems, but really the insurance model was built around fossil fuel, predictable systems and structures. Commercial agreements, this is the last one I'll focus on just now. Charter parties don't allow for rerouting to improve your wind. Yeah, it's, what is it, with all due dispatch, is that the wording? Yeah, basically you've got to go from A to B, get there as quickly as you can, safely.
Cool. Hurry up and wait.
Hurry up and wait. And actually that's a really good quote that was from the Valenius Wilhelmsen CEO. Actually said that we're an industry that does, we hurry to wait. And not the ship necessarily, but the chain. And if you think about Valenius Wilhelmsen, they actually transport cars to the US. So they rush across the ocean, burn all this fuel, fulfill the charter, brilliant. Then the cars sit for 2 months on the quayside waiting to be certified to be allowed into America. That's, from a logistics chain, that's completely crazy. Yeah. Bulkers and tankers, we don't have just-in-time delivery, really. We create it by our contractual law, but it's pulling from a stockpile, delivering to a stockpile. But why do we need to rush so much to do that? Not saying that if you put wind on, you have to slow down. You don't. You can go at the same speed with less fuel, or you can slow down and make even bigger savings. Yeah, but that's a commercial decision. Anyhow, okay, and this is my last slide that I'm not even presenting it. All of these companies, which a lot of them you will recognize, are all involved with wind propulsion projects, developing technologies with wind propulsion on their ships, certifying them, and I could probably do another 2 or 3 slides of this. Yeah, we've got some Hapag-Lloydism up there. They declared during COP28 they've got a design going on, so I can add them to the list. We've got people at Oldendorf, Cargill, K-Lines, MOL. These are very, very large companies that are putting substantial amounts of money into a technology. We're not quite mainstream. I often say this. I'm waiting for the day when I don't have to say this. We're not quite mainstream yet, but mainstream players They're getting heavily involved. And I would say probably 2024, we could probably declare wind propulsion as $1 billion industry. Yeah, we're in the high hundreds of millions already. We probably are in the billion, but I'm a conservative guy. I don't like hyperbole. So, okay. And what I've done is at the back end, I've added some slides with the technologies on. Okay, well, I won't go through those now, but I'll give the PDF to Keith and enjoy those. And we've actually got an industry report coming out in a couple of weeks. I've just submitted it to IMO, which is about 165-page long thing with loads of case studies in it. So if you haven't had enough, I'm more than happy to send you a copy of that, and we've got some bedside reading. Okay, thank you very much.
Okay, thanks, Gavin. It was a big build-up, but you didn't let us down.
Oh, excellent. Glad to do that. Thank you.
So, for those of you online, if you do have any questions, if you want to put them in the chat box, we'll sort of go through the questions if you have any. As there aren't any at the moment, we'll start here in the room. First question to Gavin. I'm sure that you're all.
I've answered it.
Well, that's true. You do go through and answer your own questions as you're going along, but Peter.
Just checking, while they're all thinking, can we just have a look at the last bits of that?
Oh, yeah, sure, sure. Yeah, sure.
Because you went through it.
Okay, yeah. So this is some key considerations around putting something on a wind assist system onto a vessel that is not designed for wind. So it talks about the rudder, the engine, the correlation between the engine getting loads of wind. So people say, oh, you're getting 30% of the energy to move the ships coming from wind, but then all of a sudden your engines are burning, inefficiently, or your rudder is inefficient. So you're losing energy. So it's optimizing that. It's as we know, a ship is a system of systems. Yeah, and this is just one system being plugged into a system of systems. But things like, for example, when the wind in the early days, simulators would just look. You'd have your computer model with a rotor, say like this, and the wind would come in and you calculate. Great. Those are in the very early days. Now is the interaction between the wind system, the freeboard of the vessel. As the wind's hitting the freeboard of the vessel, it's spiraling over the deck of the vessel. So you're losing the efficiency maybe from the first meter or two. When you've got 1, 2, 3 systems, those are interacting. Greg and I were just talking about this. You're going to have interactions between those systems. Yeah, they're going to be blocking each other. They're going to be creating turbulence. You're going to have less efficiency. So it's finding the optimal way to deal with each of the wind conditions, and a lot of studies going into this. Yeah.
Sail setting.
Yeah, absolutely. In the good old days, absolutely. Yeah.
Are the ship hulls of new ships being designed to take these rigs later?
Yeah.
Now,
Well, I've
or are
seen.
they different? I presume.
Well, no, I've seen quite a few designs that are coming through that they're thinking about this. They're softening the contours around the wind system. I mean, probably Greg would be a good person to have a chat with about that as well.
But what's going on under the water is really important.
Yeah, absolutely.
Your traditional bulk has got an awful lift to drag ratio. If you apply a side force to it, you get a hell of a lot of drag off.
Yeah, so all of that's got to be factored in.
Not designed for leeway.
Well, absolutely. So when you've got I'm starting to get into technical terms. You've got skegs, you've got dagger board options, there's quite a few options that you can have to help optimize that. When you get into this primary wing new build aspect, that's when you can really get some magic going, because you're designing and integrating the system straight in. And that's when you get things like energy harvesting, full integration into the whole system. So and then that's a rotor sail, so it just goes in very quickly into what a rotor sail is. Uses the Magnus effect, which is like a spin ball. In spin ball, was it is that a spin ball in cricket? Curveball in baseball? Is it? Yeah, it's ball.
That ball.
Yeah, curveball, right, so it's the same aspect of spinning. When wind hits a spinning cylinder or sphere, it creates a whipping action, and that's what it's feeding. Suction wing or suction sail, these actually were developed by Jacques Cousteau in the 1980s, and actually one of his team is working with one of the providers of now.
I worked with him.
That's
With Andre Maury.
all right, Andrew, right, yeah. So showing your age now.
Oh, yes.
But this has it's kind of a stubby wing that when the wind hits it, it stalls around it, and you suck in the boundary layer, and that creates extra lift. But of course, it's an active system as opposed to a passive system as the rotor sail. So you've got more moving parts. You're using some energy to gain more energy. Yeah, so there's always a trade-off there as well. Hard sail, and this one I always use. It's very simple to explain a hard sail. It's basically an A380 aircraft. Yeah, humongous thing with stubby little wings, create enough lift to lift that 800 tons into the air. That shouldn't fly. It's like a bumblebee, it just shouldn't fly. Yeah, and I've got a number of them going like this is going to fly. Basically, pretty great. I'm dumbing down decades of your experience, but basically doing that with the wind, and that creates a huge amount of lift. And of course, the racers, you know, leisure yachts people have decades and decades of information on this, down to fine granular performance. Yeah, so actually they're having to dumb it down to a degree for the commercial side of things because you don't need that amount of data. But they, you know, to get 0.01 knot extra out of your boat in an American Cup race could be, it's the thing. Soft sails and hybrid sails, they're all kinds of sails. Actually, the one behind the bar there is one developed by Michelin, and it's inflatable, so it looks like a Michelin man that's crossing the road and being flattened. But we've got all different kinds of sails there. Kites, these are either passive kites or figure-of-8 kites. And one of the leading developers is Airseas, which is a spin-off of Airbus. And they're pretty much bringing all their all of their aeronautical engineering ideas, pretty much like a drone. It operates like a drone at about 300 meters, where the wind is blowing all the time. 99.9%. And then we've got a couple of others. These are the last two. Turbines, which obviously can generate electricity, but interestingly, some designs can actually help with thrust and also break up the contours of the vessel. So when you've got a big block of wind hitting the front of the vessel, if you've got a turbine, it's actually creating a breakup of that wall of wind. And then we've got hull forms, and there's a couple of companies. This is a Norwegian company where the actual ship hull is a wing sail. It's creating this is LNG powered. It's a design, they haven't built it yet, but it's powering into the wind. The headwind they get actually creates lift and sucks it forward. Commonly known as magic. But they put a huge amount in this, and there's also Japanese companies looking at this as well. Now, what's interesting for me is if that bled into standard shipbuilding, where we actually say, okay, we're not going to get, they're talking about up to 70% by wind. But if we got 10% by redesigning the hulls of our standard ships, where we use the wind rather than fight the wind, and we don't just make it aerodynamic, we actually make it aero positive. Wow, that's exciting stuff. But I'm too old to get into that, so I'll leave that to the young guys at the back. But that could be, you know, these are some of the holy grails. Yeah, if we could actually use wind to really, really bring us into a blue skies situation, and everyone's hating now for asking me to go through that.
You were talking about aircraft wings. A lot of those now gone to glass fibre, and that's technology. How resistant would that be in a maritime environment? Because they're designed for high altitude where it's comparatively dry, and non-salty, and now we're kind of covering them with salt. So
Absolutely. This the Silent Seas one with the solid sail, that's fiberglass. A lot of the systems are a form of fiberglass. I think it's not sure all of them are using this, but I can't remember the acronym for it. Extensive testing. I'll just show you the one that's probably undergone more testing than any other, which is the MOL system, which I think I used. Yes, this one, the Wind Challenger. This system is actually retractable. It's about 30 meters plus. Well, I've been to the test site. They've had one of these on test since 2016. And these have been through right on the coast, typhoons, everything. So they've tested pretty much everything. Now, obviously, they're testing in a pure marine environment, but the materials have been very resistant and been developed. So there is a lot of material science going on. I know Greg's project got some really interesting ways they're forming and reforming the pieces. But there's one other thing I will add to that, is it's the recyclability as well. It's the circularity of this. Now, I sit on the World Wind Energy Association board, and we're starting to see the recyclability of turbine blades, which are actually pretty similar to this. You know, you're talking about something that will last about 20 years, 25 years in a maritime environment. So we are learning from them, and the recyclability is getting better now. So you're going to see lots of reports of landfills full of early wind turbine blades because they were built without that circularity in mind. The ones now are pretty much 100% recyclable. And the systems, it's not the technology to do it, it's actually the cost. And they've now found ways to do it with reasonable cost as well. So yeah, so that circularity. So it's the materials, but also creating materials that we can actually reuse and recycle at the end of the day.
Oh, yeah.
You know that was
Easy one.
oh, it's softballs. I like that. Yeah. Well,
So obviously you're gonna get every technology provider with Propulsion saying they're the best, we provide the most power, we provide the most with Propulsion. Where does the IWSA stand currently in its efforts to create the equivalent to say what automatic use, so like a drive cycle, MPG, MPGE, so that a ship owner can go, okay, well, this gets me this much power.
You said it was going to be easy.
I hope none of my members are actually listening. This is at this early stage of development. So I don't like to use the word Wild West, but I'll use Wild West.
Yeah.
Is we've got 14 developers already in market, another 20 plus very near market, and another 30 to 40 developing systems. And even the ones in market are developing new iterations of the system. To standardize and have an appraisal system for that as an association we could mandate, that's a bit of a way off yet. Okay. Having the standard validation approaches, we're working on those. And there are consultants now moving into this area with varying quality, and that's one of the issues. And we may well get into maybe standardizing or certifying those guys in the future, and saying, yeah, this guy's got the IWSA stamp, talk to him. The other guy doesn't have it, no comment. But that is a problem. Also, one of the issues is the spread from class societies. So class societies, as we know, have many areas of business interest, and this is one of them that's being identified, and almost all the classification societies now say, well, we can also recommend what you use. We can assess it for you. IACS, for us to step in and do something that maybe IACS could do would be sort of churlish, I guess. Yeah, but we're very much involved with those discussions, and our if you like, our mantra is robust, transparent, and standard. And if we can maintain those three areas, even if it's not IWSA delivered, we will try to ensure that as much as possible. So I've got a chair for a work group. Thank you for volunteering.
Just something from somebody online, John Stott, who says that they're using GR3 aluminium in our wings at SPS. It has approval in principle with the LR. And it's now with the LR for plan approval, and our test rig is to be installed next month.
Yeah, so
as a follow-up.
So thanks, John. SGS is Smart Green Shipping, and they're in Glasgow, or in that region. That's where their test rig will be. So next time you're up in Glasgow, Keith,
February.
University of Strathclyde, yeah, get in contact with Diane, and you can pop along and have a look. Yeah, but yes, so FLP, yeah.
Okay, quick one. I think that this technology potentially might have impacted the ship design or the existing rule for the ship design. For example, I understand this technology will induce sort of lateral sort of maneuver force constant all the time. Does it mean our existing, for example, rudder design requirement or rule is it still adequate, because they need to much handle much more
So
frequently?
yeah, so everything is a little bit of a trade-off. Yeah. Okay, so these systems, they're not rigid, they move. So the system on your, the operating system, if it says, right, we've got too much heat on the vessel, you just depower your system and you go back. So that you for example, you'll have a certain tolerance level for heat, okay, on the vessel. Say you don't want to go above 3% or 4% of
So
it.
they have some intelligence.
Yeah, they're all computer operated. Even back in the 80s in Japan, when Japan put on 8 of these systems onto the Jamba systems on Japanese tankers, it was all computer operated even back then. And there's actually a film, if anybody's interested to see that, there's a film online from '86, and they've got the computer system. But yeah, so basically you say, right, these are the tolerance levels that we're willing to, or that class has said you cannot heal more than 4 degrees. So the computer system will notice that you're healing 3 degrees, it will start to depower the system, drop the wind out of it, and you just correct yourself. Or, and this is where the early systems are not fully integrated yet. So they will be more, where you have your rudder management, the management of the rudder, the engines, all of that integrated with the wind system itself. That system for a new build is easy to do, for a retrofit is more challenging, but we're getting there, we're moving closer and closer to that.
Actually, they might, if there's huge benefit introduced by this technology, might be existing technology, rudder, for example, can be, adapted
Yeah, of course, it is. And it
to
is,
compensate for that
yeah, it is.
additional requirement.
All of the companies that are getting involved, they're very much aware of what they want to get out of the system. So if you want to optimize the system, then you're going to have to make changes to the vessel. If you're happy to get 7% or 8%, like this one, I think provides about 8% power, and they're happy with that, that's fine. We don't want to make any changes to the vessel. If they were then to say, well, actually, we kind of like to really optimize and push it over 10%, then you're going to have to start looking at your hull, your rudders, your engine system. So there's always going to be trade-offs, but you're absolutely right for pointing that out. But these guys are putting in a huge amount of money and time into the analysis.
There's quite a lot of studies now on things like side force and the impact and the effect of yawing versus rudder and all of those types of things, and then working out the optimum position of the wind propulsion device on the vessel to get the most out of it. And it varies with the different types of systems that you put on the vessel. So it's a pretty complex thing, but we're getting a lot more understanding.
And the digital twin frameworks are there for a lot of standard hulls and exceptional hulls. But also, as we talked about before, with AI, you suddenly what one iteration of that design cycle used to take maybe a fast computer might take a few hours, now can be done in seconds.
Yeah, I'm thinking potentially they might change the loading profile of vessel.
Yeah.
For example, ship structure may be fatigue and life was different. Not just fatigue, particular rudder component,
Absolutely.
fatigue strength will be different.
And all of with these demonstrators, a lot of that we've got simulation, those are good. But of course, those are not real ships. So the more I'll give you an idea. I'm sorry, Keith, you're standing there, with shut up, yeah. Well, I'll give you an idea of the amount of time that one ship's been in operation where this data has been collected. So the E-Ship 1 is probably the first modern ship. And just a second, I'll just go back. I think I have a picture of it. Oh, it's not working anymore. That's my high tech. No, okay. E-Ship 1 has 4. You may have seen it. It's got 4 rotor cells. That was launched in 2010. So it's had 23 years of operation. It was out of operation for about 6 months. I mean, its engines changed, not the rotor. So it's not 22 years. That's so I'm tired. 13 years, yes, or 12 to 13 years. So that is tens of thousands of operational hours. All of that feedback is going back to a company called Flettner Rotor. They're integrating that into the designs of their system. Norse Power, I think their first ship was in water 2014, so nearly a decade in operation. So again, the understanding of this from an operational point of view, we haven't been one full life cycle of a vessel yet, but that information is feeding back, and especially the designers in places like Marin and Syntef, HSVA, these guys have all of this data coming back in projects that they're working on. So yeah, is it? Do we understand everything perfectly? No, not at all. But the body of data is right. And don't ever ask me about my maths.
Well, I think we're going to go through the hands up there. One of you, I will.
So following on this, you were saying that among this ship, there's many others that there has been implemented like wind propulsion systems already. And I was wondering, like, how does it compare, like the real performance once implementing a real ship with the predictions and the calculations before actually implementing a ship? Is it like much similarity, or is it a big difference between?
That's a good question, and actually we're going to be, I'm very interested to see some coming from a couple of ships that have been put in that they're talking about large amounts they were installed this year. Yes, pretty well aligned, especially the smaller systems, pretty well aligned, sort of at the moment 5, 8, 10%, but these are, remember, these are on ships that don't change their operation. They're not being operated as Windships. They just put a couple of rotors on and then integrate that. The canopy, which was the one I talked about with the Ariane rocket supplying. I'd like to go back to the picture, but me a dumb thing. I'll keep talking the moment we get back. I've had a meeting with them just before Christmas. And they completed a couple of voyages. And they were absolutely. Oh, there we go. Oh, perfect. There we go. So we'll just go back to. Okay, the E-ship one is the one in the left, bottom left. Small one, sorry, and the canopy that's the top left. Okay, so I'm just talking about the canopy now. They were absolutely delighted with the performance that they had on the 2 or 3 runs that they've had, beyond their expectations. Now, that's a technology provider telling me the salt, but I usually I know when the guys are really happy, and they were absolutely delighted. So yes, I mean there's 2 things. There's one, you're a ship owner, I want to get your business. Do you believe me when I tell you what? No, of course you don't. Unless you're an idiot, you're not going to believe me. So I will probably give you the better performance figures because I want to impress you. Okay. Now, from an association point of view, we actually try to temper that right down. So it's much better to under promise and over deliver. Now, the third party assessments, almost all of the ones that I'm seeing now, pretty well aligned. You know, the modeling has got much better. And that also, and the performance of these systems is getting better. We're understanding the systems better. The design of them is getting better. The materials are getting better. And also the cost is starting to come down because of improvements in design application. So you're actually getting better. So it might be cheaper, better performing, so a better ROI for you as well. But yes, I would say that they are aligning better. However, I do on occasion hear someone saying, we'll give you 30% on a bulker. I'm like, really? Prove it. You know, I've seen 10%, I've seen 12%, you know, being proven. Okay, that's great. There is one vessel, a ro-ro, that's in operation in the North Sea, where they're getting around 25% from 2 very large roads. So it's not third-party validated, but it's on very windy routes. But the interesting thing is actually about 20 to 30% of the time, ships operating only on, that's averaged out. But all of these numbers, when you use percentages, you basically lose because it's not, it doesn't really work that way. But when the ship owner wants to know how much fuel I'm going to save, that's my investment choice. They want to say simple, how much fuel will I save with the system? And it's always, okay.
Yeah, then we have one last question.
You said winds can basically go with any alternative fuel as well. Since you're working towards the same goal, is both industries kind of working hand in hand, or is there pressure on alternative fuels to kind of slow you down because you're the competition?
I don't know who's on the line. I don't know who's in the room. We get along things. No. Actually, I mean, from our point of view, we work very collaboratively. So we are completely open with what we're doing. Now, the alternative fuel guys are so busy arguing with each other, or trying to get market share. What we're saying is we actually reduce the market size. So maybe all of them hate us. Okay. However, in a sense, if we're reducing that size, that actually allows us to get higher percentages into the market quicker. Potentially, you're actually reducing the dependency on the fuels, so there'll be more bunkering areas. You're increasing the range of the ship by having the wind on, so you can actually go to places that are further away that can bunker alternative fuels, but maybe not economical to burn fuel to get there. So there's lots. I mean, I'm not an economist. I have a bit of a background in that, but there's lots of variables that float around. But yeah, I mean, a lot of ships that are being designed at the moment are, if they're wind plus an alternative fuel. But I just want to say one thing. We're hearing a lot about alternative fuels. There's 200 ships that are coming out of yards that are alternative fuel ready. Will you burn methanol that's twice the price? Probably not for your business. Unless you're charging a surcharge for your customers. But remember that methanol isn't green now. There's only 1% of all methanol in the world is green. Yeah. So we got the ships that are ready for the alternative fuels, but those alternative fuels will probably take 20 years before they're green, and also probably 10 to 20 years before they're available. So, and I'm not denigrating this at all, but you know, my driveway is Ferrari ready, doesn't mean I'll ever have a Ferrari. But so I think what we need to do, and what we have actually asked, and this has been a public statement, we asked for a strategic review within shipping. What are we actually going to be doing? Now, green corridors, okay, great, yeah, awesome. But is the fuel going to be available at a price that's affordable, or will that be snapped up by other sectors? You know, aviation, biofuel, methanol, industrial process. They want to green their fuel. They want to green their logistics. Yeah, or their supply chain. So we're going up the competitive ladder. HFO, nobody wants it. How much do you want? You can have it cheap. LNG, we saw what happened in 2022 when supply became the price went through the roof. Because what are you going to do? You're going to restrict it. Oh, thank you. Use some things. Are you going to heat people's houses and keep the lights on, or are you going to deliver them their Christmas present? You know, of course, we need to move the oil to be able to, you know, or the energy. But the problem is that shipping has always been, or in the last 45 to 50 years, has been a residual fuel market. Now we're going up the technology level, and we're going up the refined fuel level, and that creates stresses. Yeah, that's my political approach. But yes, so I think there's a big debate around this. There will be huge amounts of new fuel available in developing countries, for example, Namibia, Chile are looking at massive amounts. Australia as well, not developing, but well, a bit developing country. Anyway, but you know, again, what industries will grab that? And frankly, shipping has never been willing to pay high prices for fuel or energy. In the past, we're going to have to get used to that.